Hi, welcome to this lecture titled Defining Functions. We'll first talk about how you use functions in your code and then how you define your own functions. And then we will look at some examples of implementing mathematical functions as a module. And then we'll talk about how you use functions to organize your code. And then we will discuss passing arguments of different types to a function and also returning values of different types from a function. And then we will discuss some special kinds of functions, such as filter, lambda, map, and reduce functions. So why do we need functions in our program? Well, we need functions to allow us to transfer control back and forth between different pieces of code. So that's one use for functions, just to transfer control back and forth between different parts in the program. And then functions allow us to clearly separate tasks within a program. So each function typically represents a logical unit, right? And then functions also allow us to reuse code. So for example, if you write a function that calculates the square root of a number, it's just implemented once and then you can use it wherever you need the square root calculated, right? So functions allow reuse of code. Now functions are not a new concept to us. We saw functions when we discussed HMMM programs, and we discussed some of these advantages there as well. All right. So functions allow for programs that are easily maintainable because you have the logic of a certain computation implemented exactly in one place. So it's very easy to maintain and debug and so on, right? So we discussed these things back when we talked about functions in HMMM. So it's the same idea here, right? So we'll talk about how you work with functions in Python and how you define your own functions and so on. Okay. So how do you define a function in Python? So here's the most general syntax for defining your own function. You put the keyword def followed by the name of the function that you're implementing, and then in parentheses you put the parameter names, right? So these are the inputs to the function or the parameters of the function. So you can have 0 or more parameters separated by commas. And then you have a colon, and then what you have is the body of the function, which is basically a collection of statements. And these statements are indented by some number of spaces. Okay? Again, remember that indentation is what denotes block structure in Python. Right? So you have the def keyword followed by the name and then the parameters, 0 or more of them separated by commas in matching parentheses, and then colon, and then the function body. All right? So let's look at the anatomy of a function in some detail. So the first line that you have in a function definition is what we call the signature of the function. And it consists of the def keyword, the name of the function, and a sequence of 0 or more parameter values separated by commas and enclosed in parentheses, and a colon. Okay, that's the first line. And then you have indented statements which make up the body of the function. Right? Now the function body can contain a return statement, which is what lets you transfer control to the point where the function was called. All right? And the return statement typically returns the result of the computation as a return value. Okay, and that value is returned to the caller of the function. So it's the return statement that you use to transfer control from a function to the place where the function was called. All right. Here is an example of a function that tests if the argument n is prime or not. Okay, so the name of the function here is prime. It takes a single parameter n, and we want to test if n is prime or not. So this function is going to return true if n is prime and false otherwise. And what we have here is the body of the function. So let's go through this carefully. In the first line here, we test if n is less than 2. And if so, we simply return false because in that case, n is not a prime number. So when we say return false, we are immediately out of the function, all right? And this value is returned to the caller. Whoever called this function is prime. Okay, so that's what we do when n is less than 2. Simply return the value false to the caller. Otherwise, we say I equals 2, we define a variable I and initialize it to 2, and then we test. As long as I is less than or equal to the square root of n, so convince yourself, and we have seen this before, this expression is the same as saying I less than or equal to the square root of n. Right? So if I is less than or equal to the square root of n, we test if I evenly divides n or not. And if so, in which case this expression is going to be true, we again return false to the caller, saying that the number n is not a prime. Again, when we return false from here, we are immediately out of the function and back into the place where the function was called. Okay, but what if I does not evenly divide n? Well, in that case, we increment I by 1 and repeat this process. As long as I is less than or equal to square root of n, we test if I evenly divides n or not. If not, we keep going. Right? And if you find an I that evenly divides n, you return false right away. Okay? And then if you're out of the while loop, and if you get here, that means you have exhausted the while loop, and at this line, I is strictly greater than the square root of n. And here you conclude that the number n was a prime number, and you return true to the caller. Okay, so that's our very first example of a function definition in Python. How do you call a function? So we know how you define a function. How do you call it? Well, this is something that we've seen before. We have made use of functions so far in Python, so we know exactly what the call syntax is. So you simply say the name of the function followed by the arguments in parentheses separated by commas. Okay, so here we are calling the function is prime with a single argument 31, and the function then returns true or false. In this case, it's going to return true, meaning 31 is a prime number. Okay, so that's basically the syntax for calling a function. Name of the function followed by the arguments to the function separated by commas and in matching parentheses. Okay. Now, when the function call is part of an expression, such as here, then the function computes a value, and that value is used in the place of the call in the expression. So what do we mean by that? Notice here on the right hand side we have an expression, and that expression is basically a function call. So we are calling the function sqrt in math with the argument 3. So that function is going to return the square root of 3, which is used in place of this call. Right? So it is as if x is then replaced by square root of 3. Okay. So in other words, functions that return a value can serve as an expression. So you can use them wherever you need an expression. What about a function call that does not return a value? Well, in that case, that function can only be used as a statement. Right? So here is an example. stdio.writeln takes a message and simply writes it out to the terminal. It doesn't return a value, so such a function call can only be used as a statement because it doesn't have a value, so you cannot use it as an expression. Okay. Let's look at a concrete program where we work with functions. So this program is called harmonicf.py, and what it does is it writes to standard output the harmonic numbers specified as command line arguments. Okay. So what is a harmonic number? Well, the nth harmonic number is denoted as h sub n, and it is simply calculated as the sum 1 plus 1 over 2 plus 1 over 3 and so on, all the way up to 1 over n. And we have seen this before. Okay, we even wrote a program that calculated the nth harmonic number. It's the same program here almost, except that things are organized using functions here. Okay, so let's look at the program carefully. We import our usual modules stdio and sys, and then we have two function definitions. The first function, harmonic, is what calculates the nth harmonic number as this sum. So it takes a single argument n, so it's a function of one parameter, and then it sets total to 0, and then I goes from 1 all the way up to n. and then we simply say total equals the current value of total plus 1 over I, right? And then finally we return total. Okay, so that's how we calculate the nth harmonic number inside of this function. And now notice here this float was unnecessary. In fact, even 1.0 is unnecessary here. Here you could have just said 1 divided by I, because in Python 3 this single slash stands for floating point division. Okay, so that would have worked. Alright, so that's the harmonic function. Now let's look at the other function, main. Okay, main is going to serve as the driver or the orchestrator. Okay, so what do we mean by that? Well, the first thing that we do in the main function is we print a message saying that we are inside of main. And then what we do is we have a loop that goes from 1 all the way up to the length of sys.argv. So we're basically looking at the command line arguments here, all of them. All right, and for each such command line argument, we turn it into an integer. So sys.argv of j, okay, is turned into an integer and assigned to arg. Okay? And then what do? We simply calculate the harmonic number for that value arg. Right? So we call the harmonic function, which we talked about, giving it arg as an argument, and that returns the harmonic number which is assigned to value, and we simply write the value out. Okay, so if the command line arguments, for example, are 1, 2, and 3, then j is going to go from 1 all the way up to the length of sys.argv, which is 4, because it includes the name of the program as well as the 0th argument. So what are the possible values for j? Well, it is 1, 2, and 3. Right? So we first get the first command line argument 1 as an integer, which is stored in arg, and then we simply call harmonic with the argument 1. So we are asking for the first harmonic number, which is returned by this function harmonic and assigned to value, which gets printed. So we write the first harmonic number, and then in the next iteration j is 2, we get the second command line argument, which is 2 as an integer, calculate the second harmonic number, print it, and then in the last iteration j is going to be 3, the third command line argument is 3, so we calculate the third harmonic number and print it. All right, so that's what the main function does. So as you can see, the main function is simply responsible for getting some input from the user, such as these guys, and calculating the corresponding harmonic numbers and printing the result. But keep in mind that main is not actually calculating the nth harmonic number. That's the responsibility of this function. All right, so this is the logical unit that calculates the nth harmonic number. Main simply serves as the orchestrator, receives input from the user and then calls harmonic to print nth harmonic number and prints the result. Right? Okay, so that's the main function. So the last thing that we need to talk about is this bit here. Okay, so this conditional is what is responsible for launching main, right? Because main is just a function definition. This function is not going to kick in unless someone explicitly calls main. So who's calling main? Well, main is being called right here, but notice that it's being called conditionally. This main gets triggered only when this variable has exactly that value, in which case this Boolean expression is true, so main gets launched. So the question is, first of all, what is this strange looking variable, and when does it take on this value, right? So this variable has a special status in Python, right? It is a special variable, and hence this special name. It's called underscore underscore name underscore underscore. And when you run this program the usual way by saying Python 3 harmonic f.py and any arguments, this variable is assigned a value which is exactly that. Okay, so this variable has precisely this value only when you run the program as such on the terminal by saying Python 3 and the program name. Okay, so when we run this program as such, this expression is going to be true because name has exactly that value and main gets launched. And what does main do? Well, it simply does what we talked about before. Receive input from user, calculate the nth harmonic number, and print the results. All right. So this is how we are going to organize our programs going forward. We're going to have a bunch of functions, and then we'll also have a driver function. And usually we'll call it, and it's a good idea to call it main, which makes it very clear that it's the driver function, the entry point. Right? So this function is also called the entry point. Okay? And you don't have to call it main. You can call it whatever you want, but main is a good name. There are other languages where the entry point function has exactly like a specific name, but not in Python. You can call it whatever you want, and just make sure that you trigger it as such. Right? So you can call it whatever you want. If you change this name to something else, change this to that name. Right? Okay. Now, so when a program is executed directly by the Python command, which is as such, then the name attribute is set to main. So that's what we just discussed. But if you go into the Python shell, so instead of running it as such, if you go into the Python shell and if you import this program, harmonic F, as such, in that case, notice that main is not triggered. Why? Because when you import the module, this name is not set to that value. Okay? And as a result, when you imported the module, main didn't get launched because this condition turned out to be false. Okay? And it's clear that main wasn't launched, because if main was launched, you'd have seen this message here. But we didn't see this message here, right? Whereas we saw it here when we ran it as such. But when we import it, we don't see that message. All right? So now when you import this module, what if you want to calculate the harmonic number, the nth harmonic number? Well, you do that by saying harmonic F, which is the name of this program, dot harmonic, which is the name of this function. So that's the standard syntax, right? So you put you say the module name dot the function name. So that's what we are doing. So we import the module and then we say module name dot function name, and then give any arguments. In this case we say 4, and the program comes back with the 4th harmonic number. Okay, so keep this in mind. When you run the program as a standalone program, this special variable gets this value. All right, so you can use that to trigger the entry point function, which is what we are doing here. But when you import a module inside of the Python shell, or inside of a program for that matter, the name variable of that module is not set to this value. Okay? So that's that. Now, a Python function can have more than one parameter variable, and that is shown in this example. So here we are defining a function called hypot for hypotenuse that takes two arguments, a and b. So there are two parameters here, and it simply calculates the length of the hypotenuse of a triangle whose sides are a and b. Right? The body is extremely simple. We simply return mat.square root of a square plus b square, because that's the formula for the hypotenuse. Okay. So what we are saying here is that you can define functions with any number of arguments. And then we can also define any number of functions inside of a .py file. All right. So here is an example of two functions sitting inside of some .py file. Okay. So the first function is called square. It takes a single parameter x and returns the square of that number. So x squared. And then here we have another function hypot, which is exactly what we have here. But it's implemented slightly differently. So in hypot, we want to return the square root of a square plus b square. Okay, so instead of calculating a square here explicitly as a times a and b square explicitly as b times b, we are simply making use of this function because that calculates the square of a number. So why repeat the logic, right? So this is good programming practice. So what we are saying is we return square root of, and to calculate a square, we simply call this function here square with the argument a. So that returns, so this is going to return a square. And then we make another call to square giving b as an argument, and that returns b squared. And then you simply add them up and take the square root and return that value, right? Okay, so we can define a .py file with any number of functions. Now we can put return statements in a function wherever we need them, as in the case of the isPrime function that we talked about before. So if you recall, there were 3 return statements there. Okay, so we can have any number of return statements inside of a function. Now a function can provide only one return value to the caller. Okay, to be more precise, it returns a reference to exactly one object. Okay, but that object could be an object of any type. It could be an integer, a boolean, a float, or it could be a string, or it could be a list or a dictionary or what have you, right? So you can only return one value, and that value, to be precise, is a reference to one object. Okay, so keep that in mind. What is the scope of a function's local and parameter variables? Well, in a function, you typically have parameters. What is their scope? Well, their scope is the body of that function, so they are not visible outside the function. And the scope of the local variables inside of the function is again specified by the block in which it is those variables are defined. Right? So, for example, in this function square, what is the scope of this parameter x? Well, it is simply this function. So this x is not visible in this function. Likewise, the scope of these two parameters a and b is the body of this hypart function, and they are not visible inside of square. And if I happen to define a function such as f with some parameter a, and then if I define some local variable b equals, let's say, 5, the scope of b is all the statements that follow this statement. Okay, and b is not available outside of the function, right? Now, the scope of variable defined in global code, which is known as global variable, is limited to the .py file containing that variable. So you can have a file, a .py file, and you can define some variable outside of any function inside of this .py file, such as x equals 5. Now that's a global variable that's visible to all the functions in the file, but it is not visible outside of the file. Right? So that's what a global variable is. Now it's always a good practice to avoid global variables. Okay, having global variables in a program just leads to all sorts of problems. So it's best to avoid global variables. A function may designate an argument to be optional by specifying a default value for that argument. Okay? And here's an example of that. So this function here calculates what is called the nth generalized harmonic number of order r. Okay, and that is calculated as this sum here. Okay, so the nth harmonic number of order r is calculated as 1 plus 1 over 2 to the r plus 1 over 3 to the r, and so on, all the way up to 1 over n to the power r. Now when r equals 1, what do we have? Well, h n sub r is simply our good old nth harmonic number. So convince yourself of that. So you just set r to 1. This sum on the right hand side reduces to the sum for the standard harmonic number. Okay. Now let's look at this function and see how it implements this generalized harmonic number. Well, it has two parameters, n and r, and notice that we have assigned a default value for r as 1. Okay, so what this means is that someone can call the harmonic function without specifying a second argument, in which case that value defaults to 1. Right? So if the user only gives the first argument and not the second one, R is defaulted to 1, and harmonic in that case is calculating the standard nth harmonic number. Okay, but the user can specify a second argument, in which case that's the value that is used for R. All right. So let's go through the code. We initialize total to 0, and then I goes from 1 all the way up to n, and then we simply say total equals the current value of total plus 1 divided by I to the power R. Okay? Because each term is 1 divided by I to the power R. Right? And then finally we return total. So with this definition, harmonic of 2, 2 returns 1.25. Why? Because this is basically calculating the sum 1 divided by 1 over 2 to the power 2, because R is set to 2. So what is this? This is 1 plus 1 over 4, which is 1.25. All right. What about this one here, harmonic 2, 1? Well, that is the same as harmonic 2, because when you specify a second argument as 1, R equals 1, and if you don't specify the second argument of 1, R defaults to 1. So both harmonic 2 and harmonic 2, 1 calculate the same sum, which is 1 plus 1 over 2, which is 1.5. Okay. Now Python allows what are called named arguments, which allow you to specify the arguments to a function in any order. Okay, so for example, we can call harmonic by naming the arguments as such. So you can say harmonic R equals 2 and n equals 3. So notice in this case we have flipped the order. We are passing R first and n as the second argument. But when you do that, when you change the order, you have to specify the name. Right? And this is nice, because then you don't have to remember or pass the arguments in a certain order. You can pass them in any order as long as you know the names of the parameters. Okay, so this call is exactly the same as saying harmonic 3, 2. Okay. Now Python supports what is called functional polymorphism, which means you can define a single function for use with objects of different types. Here is an example. We discussed the square function before. Okay. Now if square is called with an integer argument, then square returns an integer result. So saying square of 4 is going to return 16 as an integer, but saying square of 4.0 is going to return 16.0. Okay, it's a floating point number. So what we are saying is that square is able to adapt itself based on the type of the argument, and that's what we call functional polymorphism. Now let's talk about implementing some mathematical functions as a module. So the mathematical functions that we are going to consider are the Gaussian probability density function, which is the famous bell curve. So here we are looking at the Gaussian PDF, the probability density function, or the bell curve. And that is defined by the formula phi of x equals e to the power minus x squared divided by 2, the whole thing divided by the square root of 2 pi. Okay, so this is the formula for a bell curve that has mean mu set to 0 and the standard deviation set to 1. Right? So that's the standard Gaussian PDF. But what if you want, what if you're looking at a Gaussian PDF that has a certain mu and sigma, which are different from 0 and 1? Well, in that case, you can still use this formula. All that you need to do is adjust the input to be x minus mu divided by sigma, right? and then you use that as the argument to this function phi. Okay, so you simply take the input x, subtract from that the mean, and then divide that expression by the standard deviation and give that as the argument to the function phi. Okay, the standard PDF, and whatever is returned by standard PDF, you divide that by the standard deviation. Okay, so that's how you work with an arbitrary Gaussian PDF with mean, mu, and standard deviation sigma. Okay, so what are we doing with these functions here? Well, we are basically calculating this number here for a given value of x. All right, so that's what we're doing. Okay, now let's talk about the standard Gaussian cumulative distribution function, or CDF. Okay, and that's the curve that is shown here. So how is this related to that? So let's say that you're looking at the scores on a standardized test such as SAT. Okay, so the scores there can be expressed or can be described by a bell curve, the distribution of the scores, and that bell curve has a certain mean and a standard deviation. Okay, now let's say we want to calculate the percentile score of a particular student who took that test. So we want to figure out how many what's the percentage of the population that took the exam that scored less than that particular student. So we want to figure that out. So let's say that we have a student that scored this much on the standardized exam. So we need to figure out the percentile score for that student. So what we calculate in that case is phi with a capital phi of that value z naught. Okay, that's the value that we are interested in, and that point gives us the percentile score, meaning the percentage of the population that scored less than that student. So what and how does that value relate to the PDF, the Gaussian PDF? Well, it is simply the area under the bell curve to the left of the point z naught. So this z naught is right here. So we simply calculate the area of the curve to the left of z naught, which is shown by the shaded region, and that area is this value, capital phi of z naught. Okay, so if we want to figure out the percentile score of this student, then we are interested in this point here. And what is that point? Well, that let's call this maybe Q. Okay? So we are calculating capital phi of Q, that's the percentile score of this particular student who took the test. And how does that relate to the curve? Well, it's project Q upwards all the way here, and in that case we are interested in this area under the bell curve to the left of Q. Okay, so that's what is calculated by the CDF function, or the cumulative distribution function. Now, unlike the PDF, there is no formula available for the CDF, but it can be approximated using this formula here. So we say that capital phi of z, okay, the CDF of z is simply half plus the PDF. So this is little phi, which is this guy here, all right? So little phi of z times this sum, right? It's an infinite sum, z plus z cubed divided by 3 plus z to the 5 divided by 3 times 5, and so on and so on and so on. Okay, so for the PDF we have a nice formula, whereas for the CDF we only have an approximation. And it's these functions that we are going to implement in the program that we will look in the next slide. So this program is called Gaussian.py, and it implements the two functions that we discussed in the previous slide, the Gaussian PDF and the Gaussian CDF, right? So what does it take for input? It takes 3 command line arguments as floats. These are z. So z might be the score of a student on a standardized test, and then mu and sigma are the mean and the standard deviation. So those could be the mean and the standard deviation of the scores on a standardized test, right? Okay, and then we use those arguments to test the phi, so this is little phi and phi, capital Phi functions, right? And then we simply write the results to standard output. And the result that we write is the percentile score of this particular student, meaning how many students, what fraction of the population scored less than this particular student on an exam where the scores had that for mean and that for standard deviation. Okay, so let's look at the code. We import math, stdio and sys, and then we have this function called pdf that implements the Gaussian pdf function. Okay, it has three parameters, x, mu and sigma. Notice that mu and sigma are optional arguments. So when the user doesn't supply a value for mu and sigma, they default to 0 and 1 respectively. So if I simply say PDF of some number, let's say z, then I'm calculating the standard PDF, all right? Because in this case, since I didn't specify the second and the third argument, the mean is 0, the standard deviation is defaulted to 1. But if I want some other mean and standard deviation, I can specify as the second and the third argument, right? Okay, so how do we implement the function? We first say x is x minus mu divided by sigma, right? So we are simply adjusting x by subtracting the mean from it and dividing that by sigma. Okay, so that's x. And then we simply implement the formula for the standard Gaussian PDF, which is e to the power minus x squared divided by 2. So exp is a function, so math dot exp of some number x is the same as calculating e to the power x. Right? So what we are calculating here is e to the power minus x squared divided by 2, and that is divided by the square root of 2 pi. All right, so recall the formula from the previous slide. It said phi of x is simply e to the minus x squared divided by 2, the whole thing divided by 2 pi, right? And then we divide that whole thing by sigma, okay? Because that was the formula for a general Gaussian PDF with inputs x, mu, and sigma, right? So that is simply given as phi of x minus mu divided by sigma and the whole thing divided by sigma. Okay, so that's what we are doing. Okay, and we return that value. So that's PDF. What about CDF? So CDF again has three parameters, z, mu, and sigma. Here again, mu and sigma have default values of 0 and 1 respectively. So if one doesn't specify the second and the third argument, we are simply looking at the standard CDF with mean 0 and standard deviation 1. So what's the implementation? Well, here again, we first calculate the standardized score. And we do that by removing the mean from z and dividing that by sigma, just what we did here, right? And then we do the following. We check if z is less than minus 8, and if so, we simply return a 0, okay? And otherwise, we check if z is greater than 8, in which case we return 1. So what are we doing here? We're saying, you have your CDF, which looks something like that. Okay, so we're saying if z is way out here, right, there is nothing to the left of it, so we simply return 0. All right, and here we're saying if z is way out here, then everything is below it, right? So we simply return 1. All right, so that's what we're saying in those two conditionals. But if these are not, if these conditions are not true, we end up here, and that's where we calculate that sum from the previous slide. So let's recall that sum. So we said phi of z, so this is capital Phi of z, is a half plus little phi of z times the sum z plus z cubed over 3 plus z to the 5 divided by 3 times 5 plus z to the 7 divided by 3 times 5 times 7 plus so on and so on and so on. Right? So that's the sum that we are calculating here. So we first initialize total to 0. So total is going to store this value. So all of that is going to be total. Okay, so let's see how that works. So we initialize term to z. So the first term is z. So that's why we say term is z. And then we initialize another variable I to 3. Then as long as total is not equal to total plus term, okay, what we do is we say the new value for total is the current value of total plus the next term. So in first time around total was 0 and term was z. So after one iteration total is going to be z, this much, right? And then we update term to say term is the old value of term, which was z, times z squared, so that becomes z cubed, and the whole thing divided by I, which was 3. So term is now z cubed divided by 3, which is the second term. And then we update I and say that I is now 3 plus 2, which is 5, right? So after the first iteration, total is going to be z, and then term is going to be z cubed divided by 3, and then I is going to be 5, right? And then what happens next? Well, we say total equals the current value of term, total equals the current value of total plus term. Well, total was z, current value of term is that, so the new value for total is z plus z cubed divided by 3. And then what happens to term? Well, we take the current value of term, which is z cubed divided by 3, and multiply that with z squared divided by I. But what was I? I was 5. So the new value for term is simply z cubed divided by 3 or it's going to be z cubed times z squared, so it's z to the 5 divided by 3 times 5, right? And the new value for I is going to be 7. 5 plus 2, it's 7. Okay. And then next time around, we update total as, let me write that here, z plus z cubed divided by 3 plus the current value of term, which is z to the z to the 5 divided by 3 times 5, and then term becomes z to the 7, because you take the current value of term and multiply it with z squared, right? So we have z to the 7 divided by 3 times 5 times 7, and then I itself becomes 9. Okay, so as you can see, we are correctly calculating total as this sum here. Okay, and this is an infinite series. So the question is, when do we stop here? When do we get out of the while loop? Well, we get out of the while loop precisely when total equals total plus term. But it's not obvious when this is going to be equal, because this guy here is constantly being incremented, right? So how is that going to equal total? Well, it's going to equal total because of finite precision. All right, so all these numbers, they have a finite precision. So at some point, total plus term is going to be identical to total. Okay, because we use finite precision to represent these terms. So this guy here cannot increase indefinitely, right? So at some point, this side is going to be exactly this value. Okay, so that's when we get out of the while loop. And what do we do outside of the while loop? Well, we calculate the rest of the formula. So we take this total, which is all of that, and multiply that with little phi of z. How do we calculate little phi of z? Well, simply call this function here, PDF, giving it z as an argument. All right, and then we simply add a half to that, that's this guy here, and return that value. Okay, so that's how we calculate the CDF. So now let's look at the main function, the entry point. So what are we doing here? Here we accept three command line arguments, z as a floating point number. So this might be like the score of a student on a test. Mu as a floating point number, that's the mean. And then sigma, the standard deviation, also as a floating point number. Okay? And then we simply write out the percentile score. And the way we do that is by calling the CDF function with these guys as arguments, z, mu, and sigma. And whatever is returned by CDF is what gets printed out. And then we have this conditional that says if name is exactly that, call main. So remember, this is how we launch the entry point function. Okay? So we first run Gaussian.py with these arguments. So that is z, that's mu, and that's sigma. So here we are saying that the percentile score of the student who scored 820 on an exam which had that for mean and that for standard deviation, we're saying the percentile score is 17%. So meaning 17% of the population scored below this particular student. Right? So this student is not a very good student. Right? What about this example? So here we are saying what the student scored 1500 on a test where the mean was that and standard deviation was that. What's the percentile score? Well, it's about 99%. Right? Meaning about 99% of the population scored below this particular student. So here's an example of your model student. Okay. Okay, so now let's talk about how we use functions to organize our code. So this program is a reincarnation of the coupon collector program that we discussed in the past, right? The only difference here is that we are going to organize our code using functions. So the program is called coupon.py. It accepts n as an integer command line argument, and that n is going to represent the number of coupons out there, the number of unique coupons. And what the program writes as output is the number of coupons that one needs to collect before obtaining one of each of n types. Right? It's exactly what we did in the coupon collector program. Okay, so the input is n, the number of types of cards that there are out there, and the output is number of cards that you have to collect until you have each of n types. Okay, so let's look at the code now and see how we organize it using functions. So we import the usual modules, random, stdarray, stdio, and sys, and then we have three functions in the program. The first function is called getCoupon, and what it does is it simply gets a random coupon. Okay, and n here is a parameter to the function that specifies the number of coupons that are out there. Okay? So we simply get a random number, random integer between 0 and n minus 1. Notice that n is not inclusive. So this value here is from the interval 0, which is inclusive, and n, which is exclusive. Okay? And we simply return that random number. So get coupon is basically simulating the process of obtaining a random coupon. Okay, what about the collect function? The collect function also receives n as a parameter, which is the number of coupons out there, the unique ones. And then what we do is we create a one-dimensional array of booleans called found. It has size n and everything is initialized to false. What is the interpretation? We are saying this is the array where we are going to remember whether a certain coupon has already been collected or not. Okay, so initially we have collected nothing, so everything is set to false. And then we initialize two variables, coupon count to 0 and distinct coupon count to 0. Coupon count is the count of the total number of coupons that you have collected so far, and distinct coupon count is the number of unique coupons that you have, distinct coupons. Okay, and then we have this while loop that says as long as distinct coupon count is less than n, meaning you still have not collected all the n different types, in that case collect a coupon, which we do by calling this function get coupon, giving it n as an argument, and whatever that is assigned to coupon. So that's going to be a random number between 0 and n minus 1. And since we just collected a coupon, we increment coupon count by 1. And then we go about checking if this is a coupon that we have already collected or not. How do we do that? Well, we go to our array found and we index it by coupon and check if that is true or false. If that is false, then we conclude that this is the first time you're seeing this coupon, so we increment distinct coupon count by 1 and we record the fact that now we have collected this coupon. So we say found of coupon equals true. Okay? But if this coupon was already collected, then we simply go and repeat this process. Okay? And we repeat this until distinct coupon count is exactly n. So when that's n, we get out of the while loop and return coupon count. Okay? So that's how collect works. And then finally we have the main function, which is the orchestrator or the entry point. Here notice how short it is, because all that it does is receive the command line argument n as input, and then it simply calculates the number of coupons that need to be collected until you have each of these n types, and it does that by calling the collect function. So main doesn't do that work itself, it simply relies on collect. Okay, so it calls collect, giving it n as an argument, and whatever collect returns is assigned to coupon count, which main ends up printing as the output. Okay, so main is extremely simple. It simply serves as an orchestrator, right? All the work is done by the collect function, which in turn uses get coupon as a helper, right? And then finally we have the usual conditional, which conditionally launches the main function, right? So when you happen to run coupon.py on the terminal, this is going to be true and main is launched. So let's look at some input and output. So we first run coupon.py with n equals 1000 and we get this for output. Then we run it with n equals 1000 again, we get that for output. The numbers are different because it's the program implements a random process. Okay, and then finally we run it with n equals 1,000,000 and that's the output. Okay, so that's a nice example that shows how you organize your code using functions. Now let's talk about passing arguments and returning values from functions. Now we can use parameter variables anywhere in the body of the function in the same way as we use local variables, right? So parameter variables are just like local variables. That's what we're saying here. And Python initializes the parameter variable with the corresponding argument that is provided by the calling code. So earlier we saw this function square x, which returned x times x, right? So what we're saying here is when we call square with an argument, let's say 5, then this parameter x is bound to this value 5, right? So that's what we're saying here. And this approach is called call by value. Okay. Now, as a consequence, if the parameter variable refers to a mutable object, and if we go about changing the object's value within the function, then this also changes the object's value in the calling code, right? So this is very important. So we need to keep this in mind. Right? So let me repeat, if the parameter variable refers to a mutable object such as a list, for example, and if the function goes about changing that that object's value, then this change is visible in the calling code. So let me illustrate that with an example. So here we have a function called exchange that takes 3 arguments. The first argument is a list, it's called a here, and then it takes 2 indices I and j. And what this function is supposed to do is exchange the values in a at the indices I and j, right? So after the function, whatever is at I in j needs to be whatever was in the index j, and vice versa. And whatever was in I in a needs to end up at the location j, right? So what we're saying is exchange simply exchanges the values at the indices I and j in the list a. So the code is extremely simple. It's the standard swap routine. So we say temp equals a at I equals a at j, and a at j equals temp, right? Now here, notice that the first argument is a list, and list is mutable. We know that. And this code is going about modifying that list, right? Because it exchanges the values at I and j inside of the list. So the function clearly modifies the list, and that change is visible in the calling code. Okay, and that is shown here. So let's say we have this function in place, and we have this list a, which is 1, 2, 3, 4, 5. And then we call this exchange function, giving it the list as the first argument, and 1 and 4 for I and j. So we want the values at the indices 1 and 4, which are these two guys. So that's I and that's j. We want these two guys exchanged. Okay, so we call this function, and then when we write a out, what we get is this list. Okay, and notice that these two values have been swapped. So 2 was here, it's now there. 5 was here, it's now there. Okay, so exchange modified this list, and the modification is visible in the calling code. Okay, so that's that. Now, when a function takes a list as an argument, what it typically implements is a function that operates on arbitrary number of objects. Okay, so let me illustrate that with an example. So here is a function called mean, and it takes a list a as an argument, and what it does is it simply calculates the average value of the elements in a. Okay, and the implementation is very simple. I mean, we have seen this before. We initialize total to 0, and then we simply iterate over the values in a. So b is each value in a, and we add that to total. And at the end, we simply return the average, which is calculated as total divided by the length of a. Right? So here is an example of a function which takes a list as an argument and simply operates on the elements of that list. Now, there are situations where you want to write a function that returns a list as a return value. And here is an example of that. So this code here defines a function called random array that returns an array of size n whose elements are random numbers between 0 and 1. Okay? So this is an example of a function that returns a list as a return value. So let's look at the code. So we create an array A using the function create1d, and it is created with size n. Since we didn't specify a second value, all the elements in this array default to none, right? So if n is 5, for example, A is simply going to be the list none, 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 and none. Okay, that's after this line. And then we say for I in range 0 through n minus 1, A at I is simply a random number between 0 and 1. Okay, and at the end we return A. So in this case, once the for loop is done, all these values are going to be random numbers between 0 and 1. Okay, so here is an example. I mean, this is an example of a function that returns a list as a return value. Now let's look at a concrete example of a program where we make use of lists as arguments and also return values. Okay, so this program is called Play That Tune Deluxe.py, and what it does is it reads sound samples from standard input, it adds harmonics to that sound, and then plays the resulting sound to standard audio. Okay, and this program is quite similar to the program that we saw before in a previous section called playthattune.py, right? The only difference is that the code is organized using functions, and there is also some additional features such as adding harmonics to a sound. Right? So let's go through the code. We import these modules, math, stdarray, stdaudio, and stdio, and then we have all these functions in place. Okay, so let's go through each function. So the first function is called superpose. What it does is it takes two lists as arguments, list A and list B, and A and B have sound samples in them. So both A and B have the same size and they store sound samples. And then it also takes two other parameters which are floats. They're called A weight and B weight. And for output, what the function returns is a list that contains the samples from A and B weighted by these values. All right, so let's see how it's implemented. So C is also a list that has exactly the same size as A or B. So we say C equals stdarray.create1d. The number of elements is exactly the same as the number of elements in A. Even B would work here because A and B have the same size. And then we say all the values are initialized to 0. Okay, and then we do this for loop where I goes from 0 all the way up to length of A minus 1, and we say the ith element in C is the ith element in A weighted by A weight plus the ith element in B weighted by B weight. Okay, so each sample in C is basically a weighted sum of the corresponding samples from A and B. Okay, if B weight is identically 0, then C is going to be a copy of the samples in A. Similarly, if A weight is 0, C is going to be a copy of the samples in B. And for any other value for these guys, it's going to be, each sample in C is going to be a weighted sum of the samples from A and B. Okay, so that's the superpose function, which takes 4 arguments, the first 2 being lists and the last 2 being floats, and it returns a list as the return value. Okay. Then we have this function called tone that takes 2 arguments, a frequency and a duration, and it simply returns an array that contains sound samples corresponding to that frequency and duration. So let's see how it's implemented. We initialize this constant called SPS for samples per second, and we set it to 44K. Okay, this is the standard sampling rate. And then we say the number of samples is the samples per second times the duration in seconds. Okay, and then we create an array called A of size n plus 1, all the values initialized to 0. And this array is what is going to store the sound samples. And what are we doing in this for loop? Well, this is where we are sampling a sine wave that has this frequency. All right. So we say I goes from 0 all the way up to n, and the ith sample is simply the sine curve discretized. All right. So mat.sine with those arguments. Okay. So we are looking at the ith sample here. So the ith sample might be something like that, the value of the sine curve. Okay, at that point. All right, and then once the for loop is done, we simply return A, the array of samples. So that's tone, which takes 2 floats as arguments and returns an array as a return value. And then we have this function called note that takes a pitch and a duration as arguments. And what it does is the following. It's first defines a couple of constants. Concert A frequency is set to 440 hertz, and then notes on a scale is set to 12. Okay? And then we say the frequency is simply the concert A hertz times 2 to the power pitch divided by notes on scale. And this is exactly what we did in play that tune.py. Right? So this formula maps a given pitch to a frequency. So for example, if pitch is 0, hertz is going to be exactly concert A, and if pitch is 12, it's going to be 1 octave above concert A. And for any other value of pitch between 0 and 12, it's going to represent the frequency of that corresponding note. Okay? And once we have frequency, we simply call tone, which is this function, to get an array of sound samples corresponding to that frequency and duration. Okay, and that's A. And then what we do is we add harmonics. Okay, so we make another call to tone, giving it twice the frequency, all right, and the same duration. So what is this array high? Well, that represents sound samples that are 1 octave above A, because it's twice the frequency. And then we do the same thing again, but this time around the frequency is half of HC. So what is low? Well, low is a list consisting of sound samples that are 1 octave below A. All right, so we have A, and then we have 1 octave above A and 1 octave below A. Okay, and then what we do is we simply superpose these three lists, A, high, and low. Okay, and we do it in 2 steps. We first superpose high and low using this function superpose, giving it high and low as the first 2 arguments, and then we use 0.5 and 0.5 for the 2 weights. Okay, so that's going to result in a list that's going to be these 2 lists superposed, and then we take that and superpose that with A. Okay, by making another call to superpose, giving it A and H as the first 2 arguments, and 0.5 and 0.5 for the 2 weights. And that is going to return a list which represents the superposed sound samples, A and H superposed, and that is what is returned by note to whoever calls note. So now let's see who calls note. So note is called by the main function. So what's going on in the main function, the entry point? Well, this is where we read input from standard input. So as long as standard input is not empty, we read a pitch and we also read the duration. Okay? Once we have the pitch and duration, we construct a list of sound samples by making a call to the function note that we just talked about. Okay? So note is called with pitch and duration as arguments. That returns an array of sound samples, and that is what we play here using the function play samples from the STD audio module. And we simply give it A as an argument. So that's going to play that particular sound for that duration. And then we go and receive the next pitch and duration and play that, and so on and so on and so on until we receive the end of file signal. Okay, in which case we are out of the while loop and we simply flush the audio and terminate the program. And then the usual conditional call to the entry point function. Okay. So let's look at some input. So here is that file lease.txt that we saw in a previous lecture, and this file simply contains information about pitch and duration. All right, and I'm just showing you the first 5 lines of this file using the head command, the head Unix command. So the first line here says play the pitch 7 for 0.125 seconds, then play the pitch 6 for 0.125 seconds, and so on and so on and so on. And if I run this program, play that tune deluxe.py with this file as an argument, as a standard input, then it's going to simply play these sound samples. All right. Now let's talk about some special forms of functions, which are filter, lambda, map, and reduce functions. In Python, functions are first-class objects, and what that means is that they're actually just data, like numbers, lists, and strings. Okay? And as a result, you can write functions that take other functions as arguments, and you can also write functions that return other functions as return values. And that's really very powerful, right? And let's look at some examples. And the examples that we're going to consider are these four different functions in Python, which are filter, lambda, map, and reduce. So let's first start with the filter function. So the filter function is a built-in function in Python, and it takes two arguments. The first argument is a function, okay? And the second argument is a sequence type, for example, a list. And what does filter do? Well, what it does is it applies this function to this sequence, and it simply filters out the items from that sequence for which the function returns true. Okay, so this function needs to be a function of exactly one argument. Okay, it's a function of one argument, and it needs to be a Boolean function. The argument of that function is basically each element from the sequence, right? And if the function says true for a particular element from the sequence, then that item is made part of the result. Right? Otherwise, that item is excluded. Okay, so that's how filter works. It simply returns those items of the sequence for which f of item is true. So let's look at an example. So here we make a call to the filter function, giving it is prime as the first argument. So this is the function that we have seen before. It takes a number as an argument and returns true or false, whether or not that number is a prime number. Okay, so it meets the criteria for being to serve as an argument to the filter function. It is a function of one argument, and it is a predicate or a Boolean function. Okay, what is the second argument? Well, range of 11 is clearly a sequence, right? Because this is the arithmetic progression 0, 1, and so on, all the way up to 10. So what is filter going to do? It is going to apply is prime on each element here and filter out the elements that are prime numbers. So that's why when I say primes here, when I try to print it out, I get a list that contains 2, 3, 5, and 7. So these are the numbers from the sequence for which is prime returns true, meaning these are the prime numbers in this progression. Okay, so that's how filter works. Now let's look at the next special function in Python. This is called the lambda function. A lambda function is a disposable function that we can define just when you need it and then immediately throw it away once we are done using it. All right? So let's look at a concrete example. So here we make use of filter again, and the second argument is a sequence. Right? It's basically the sequence 0, 1, 2, and so on, all the way up to 10. Now the first argument, where remember we need a function of a single argument and that returns a Boolean. So for that first function we have a lambda function. Okay, so the way you write a lambda function is as follows. You put the keyword lambda followed by the parameters of the function, in which in this case it's just one parameter, we call it x, and then we put a colon, and then what you have is an expression, right? So lambda function has an expression for a body. So here the body is very simple. We say x%2 not equals 0. So this clearly is a Boolean expression, right? That is going to evaluate to true precisely when x is odd, and it's going to evaluate to evaluate to false when x is even, right? So that's a lambda function. And so what does filter do then? Well, it simply filters out the odd elements from the sequence. Okay, that's why when I print odds, I simply get the odd numbers from this particular sequence. Okay. Now the thing to notice here is that once filter is done, there is no trace of this lambda function. You have no access to it. Okay, it's gone. It's disposed. So that's what we mean when we say a lambda function is a disposable function. Okay, so it had its use here as an argument to filter, but once filter is done, there's no trace of that lambda function. Okay, and we don't need it. I mean, we needed it only for the filter function. Okay. The next function that we want to talk about is the built-in function map. So map takes two arguments. The first one is a function and the second one is a sequence type. And what does map do? It returns a list of the results of applying the function f to the items of the sequence which is given by the second argument. Okay, so here notice that the return type is a sequence. Okay, and that's a sequence that you obtain by applying this function to the elements of the sequence. So let's look at an example. So here we say squares equals map of this lambda function on the sequence. So here the sequence again is 0, 1 and so on all the way up to 10. And what does the lambda function do? Well, it takes a parameter x, which is an item from the sequence, and it simply squares it. So the body is extremely simple. It's x squared. Okay. So, and what does map do? It takes this lambda function and applies it to every element in the sequence. So it applies it to 0 to get us 0. It applies this function to 1 to give us 1. It applies it to 2 to give us 4. And then finally it applies it to 10 to give us 100. Okay. So that's how map works. It simply takes this function and applies it to every element in the sequence. And here again, notice that this argument here is specified as a lambda function, so we have no trace of it once map is done. The next special function that we want to look into is the built-in function reduce. Here the function takes two arguments, f and sequence, and it applies this function f, which here is a function of two arguments. Okay, so map applies this function f of two arguments cumulatively to the items of the sequence seq from left to right, and it reduces the sequence to a single value. Okay, so reduce at the end returns a single value. Right, so let's look at an example. So here we are saying total equals reduce, where the first argument is a lambda function of two parameters. We call them x and y, and the body is simply x plus y. Right, and this function is applied cumulatively to this range, which is again 0, 1 and so on all the way up to 10. So what effect does reduce have? Well, it simply sums up these values to give us 55. Okay, so this function is applied cumulatively to the items of this sequence left to right, so as to reduce the sequence to a single value, which in this case is 55. Now think about this slight variation of this example. What are you going to get if I say some variable f equals reduce of lambda, two parameters x, y, and in the body I say x star y, not x plus y, but x star y, and then for the sequence I say range 1, 11. So what do you think f would be? Okay, so think about that. So now let's look at a concrete example where we make use of these filter, lambda, map, and reduce functions. So the example that we're going to look at is an example from cryptography. So the RSA crypto system is the most widely used public key cryptography algorithm in the world, right? And this crypto system can be used to encrypt a message without the need to exchange a secret key separately, right? So let's look at the details. So let's say you have some message X, and let's restrict ourselves to like integer messages, just numbers, right? So let's say we have some message X that we want encrypted. So what we would do is we would use the function f of x, which is given as such, x to the e mod n. So that's the function that we use to encrypt this message. So the input to the function is x, a message that you want encrypted, and the output is the encrypted message. So here, what are these guys, e and n? Well, n is simply p times q for two different large prime numbers p and q, okay, which are chosen at random. So pick two large distinct prime numbers p and q, multiply them, you have your n. What about e? Well, e is chosen as a random prime number that is less than m, and m is simply calculated as p minus 1 times q minus 1. Okay, and you choose an e such that e does not divide m. And if the e that you chose happen to divide m, just repeat the process. Okay, so do this until you find an e that does not divide m. All right, so let me repeat. So what we're trying to do here is we're trying to encrypt a message x using this function f of x. N is calculated as the product of two large distinct prime numbers p and q that are chosen at random, and then m is calculated as p minus 1 times q minus 1, and e is simply a random prime number that is less than m such that e does not evenly divide m. Okay. Now it turns out that with this function, the largest number that you can encrypt is n minus 1, and that's clear because you're modding this quantity by n. Okay, so the largest number that you can encrypt here is n minus 1. Now the two values e and n are what we call the public key. Okay, and these are things that you can share with the world. Okay, so let's say you want to exchange messages in secret with your friend. So what you would do is you would generate the public key, meaning you would generate e and n, and you would share it with your friend. Okay, there is nothing wrong in sharing the public key, right? Now let's say you get a message back from your friend that you want decrypted. So how do you do that? Well, to decrypt a message y, we use the function g of y, which is given as y to the power d mod n, right? So you decrypt y by saying y to the power d mod n. Well, we know what n is. What is d? Well, d is a number that is greater than or equal to 1 and strictly less than m. We know what m is, and d is chosen as the multiplicative inverse of e mod m. By that what we mean is we choose a d such that e times d remainder m is exactly 1. Okay, so that's how you look for this number d. Okay, now this value d is what we call the private key. All right, and this is something that you keep to yourself. You don't share this with your friend. So let's go through this again and make sure we understand this. So you want to communicate in secret with your friend, right? So let's call your friend Alice, and you are Bob. Okay, so what you do is at your end you generate n as the product of p and q, two large distinct prime numbers, and then you calculate m as simply p minus 1 times q minus 1, and then you calculate E as a random prime number that is less than M and chosen such that it doesn't evenly divide M. So these are things that you do, and you also calculate D, the private key. Okay, and the way you calculate D is as the multiplicative inverse of E mod M, meaning E times D mod M is exactly 1. Okay, so you have all these guys, and then you share the public key. So you send the public key to Alice. What are the public keys? Well, it is E and N. Okay. Okay, and now how do you decode a message that Alice sends to you that is encrypted? Well, Alice is going to encrypt the message using this formula. Okay, and she's going to send that to you. So Alice takes a message X, encrypts it, and sends that over to you. Okay, you get that as Y, and you use this formula to decrypt it. Okay, and notice that in order to use this formula, you need Y, which is the incoming encrypted message, and you need N. Well, you have N, you generated it, and then you also need D, the private key. Well, you do have that as well. Okay. So you are able to decrypt that message that came over to you from Alice, right? And no one else is able to decrypt that message, all right? Even if they get hold of the public key. So if there is someone here that is spying on your communication channel and gets hold of the public key, they cannot do anything about figuring out or decrypting the message. Okay, why? Because that would amount to taking this number N and breaking it down into its constituent primes. Okay, so if there is someone sort of like spying on the channel here, and if they get hold of the public key, there is no harm done, because for them to decrypt the message, they need to break this number N into its constituent primes. And in a real world scenario, N is chosen as a product of two very large primes. Okay, so given an N, breaking it down into their constituent primes is extremely difficult. And this goes back to what we talked about in an earlier lecture on factoring a number into its constituent primes. So that's a very difficult computational problem. Okay, so for a large N, which is expressed as the product of two very large primes, it's very difficult to decompose it into the constituent primes. All right, so that's how the RSA crypto system works. So now let's talk about how you implement this as a Python module. So here it is. The module is called cryptography.py. So it's a module that implements the RSA crypto system. So let's walk through it carefully. We import two modules, random and stdio, and then we have a function is prime that we have seen before. It takes an argument n and simply returns true if n is prime and false otherwise. So this code is something that we have seen before, so I'm not going to walk through that. And then we have this function called primes that takes a number n and simply returns the number of simply returns a list containing the prime numbers that are less than n. Okay, how do we implement that? Well, we use our filter function. So we say return a filter of is prime and range n. So range n is simply going to be numbers 0, 1 and so on all the way up to n minus 1, and filter is simply going to filter out the primes from this list and return that as the return value, right? So that's primes. What about inverse? So inverse is what computes the private key. right? So it takes two arguments, e and m, and it calculates the the private key as the multiplicative inverse of e mod m, meaning it looks for a number d such that e times d mod m is exactly 1. Okay, and remember that this multiplicative inverse needs to be between 1 and m, so we have the range that goes from 1 all the way up to m. Alright, and what are we doing here? We are simply filtering out the values from the sequence for which this expression is true. Okay, so a value that from this sequence that is going to satisfy this condition is the private key that we are looking for. Alright, and what does this index here? Well, remember that filter returns a list, right? But the inverse that we want here, it needs to be a single number, but it's very easy to get that number out of the list. We simply index it by 0. Okay, so inverse correctly computes the private key, right? And then we have this function called make encoder decoder, and that works as follows. It takes a number n as an argument, and then the first thing that it does is it picks two distinct prime numbers, p and q. Okay, and the way it does that is by using the sample function from the random module. Okay, so sample takes two arguments. It takes a list, so in this case the list is a list of prime numbers between 2 and n. Okay, and the second argument to sample is the size of the sample that you want. So in this case we are saying 2 because we just need two prime numbers. Okay, so sample will get you a sample of that size from that list without duplicates. Okay, so this sample implements sampling without replacement. Okay, so p and q are two distinct prime numbers. Then what? Then we calculate n as the product p times q. We calculate m as the product p minus 1 times q minus 1. And then we simply write a message saying that the largest number that can be encrypted is n minus 1. Okay? And then what we do is we pick a random prime number from the list of primes between 2 and m. So primes m is going to return a list of prime numbers between 2 and n, and from that we choose a random one. And the way we choose a random prime number from that list is by using the function choice from the random module. So choice simply picks a random element from the argument list. Okay, so e is a random prime number, and then we test if e evenly divides m. If so, we pick another prime number. So recall what we said before. We want an e such that it does not divide m. Okay, so we look for an e that does not divide m. Okay, and then once we have e, we simply calculate the private key as d equals inverse of e comma m. So inverse is just this function that returns the private key. Okay, and then what we do is we return a list of two elements. The first element is a lambda function, and this is the encoding function, if you remember. So this is f of x, and this function here is the decoder, that's g of x. Okay, so we return a two-element list where the first element is the encoding function and the second element is the decoding function, g of y. So now let's see how we use this module to encode and decode messages. So we go into the Python shell and we import cryptography. So this is the module that we just discussed. And then we make a call to the make encoder decoder function with n equals 100. So that comes back with a list of two elements which are function objects. The first value is the encoder function f of x, and the second value of that list is the decoder function g of y. Okay, and this function prints this message saying that the maximum number that can be encrypted is 2536. Okay, and then we use the encoder function to encode a message such as 42, and that comes back with the encoded message 2235. And then we take that encoded message and decode it using the decoder function to get back the original message, which is 42. And then we do this again. We call encoder on 1729, and whatever that is, which is an encoded message, we call the decoder on, and we get back the input 1729. Okay. Now, what are these things at the end of these numbers? L. Well, L stands for big integer. Okay. So when numbers get very large, Python turns them from integers into big integers, and big integers are usually represented with the suffix L. Okay. Now 42 and 2235 and so on, these are not that big, and yet you see a L next to them because these were obtained via calculations that involved big numbers. Okay, so if you go back to the code, you will see at places we calculate these exponents. Okay, such as this, and these numbers can get very large. Okay, so these numbers that you see here are the results that you get via calculations that involved big numbers, and hence you see L next to them. Okay. All right, so that concludes this lecture. Thanks for your time.